Welcome to Math with EJD. If you remember, we're talking about differential equations in the former playlist, and we got to a point, and I feel that it's important to really elaborate on the idea of Laplace transform because it also helps in solving differential equations. It's basically turns differential equations into algebraic expressions that can be easily simplified, simply solved, and then returned through the process of inverse transform into the time domain. So now we are here to begin to apply Laplace transform to solve differential equations, especially ordinary differential equations. So, in overview, right, just like we've always known, uh, Laplace transform helps to convert differential equations, right, into algebraic equations. So the Laplace transform is a powerful tool for solving differential equations, converting them into algebraic equations in the S domain. That's why we always have f of s. In the S domain, the Laplace transform of a function f of t is defined as the Laplace of f of t, which is f of s. That is integral from 0 to infinity, integral from 0 to infinity, e raised by minus st, f of t dt. Okay. So let's look at the general form. General form of a first order linear differential equation. Okay. So a first order linear differential equation is given as dy dt plus ay equals g of t with initial condition y of 0 equals y naught. Okay, that's a typical first order where a is a constant and g of t is a given function. Okay, now how do we apply Laplace theorem, right? Applying the Laplace transform. So using the linearity property, using the linearity, no, in the second video, we looked at the properties of Laplace transform. Using the linearity property of the Laplace transform, and the differentiation property, and the differentiation property. So we see that the Laplace of, okay, I guess I can switch here now. So the Laplace of dy dt, or y prime if you like, or y dot, is equal to s ys. Okay, s ys minus y of 0. So in that case, we transform both sides. We transform both sides. And then we have, for the left-hand side, right? You have dy, you have, where's the equation again? Yeah. So you have dy dt plus ay equals g of t, right? So here you have for dy dt plus ay equals g of t, with all the y of 0 equals y naught equals y naught. So we have the Laplace of dy dt. That's the linearity applying now. And the Laplace of ay. And then the equals Laplace of g of t. Okay. So that transforms to, for dy dt, we know that's going to be s ys minus y of 0 plus, when we come here, it will be a times the Laplace of y. Or yeah, okay. Or better still, I can just take it slow and then just do this. The Laplace of y prime prime. I mean the Laplace of y prime first order plus a, the Laplace of y. When we bring out the a, and the Laplace of g of t, which is a forcing term, external force. So y prime here just becomes s ys sy of s, that is, minus a, then the Laplace of y itself normally would just be the Laplace of y is y of 0. Okay, just have is that y of 0? No, I have not completed the first one. So for this first part, right, it's sys minus y of 0. Okay, that's the first part. For the second part, we have a, the Laplace of y itself is just y of s. Okay, and coming to the right here, g of t just becomes a particular g of s. So, okay, now with that in place now, we can now collect all the ys's together. Okay, so we have s ys minus y of 0 plus a ys. Hope my y, I'm not writing this y well. Maybe I should find another way of writing this y. So this is sys minus y naught, of course, because we have that. Then a ys equals g of s. So we are looking for ys basically. So we have ys is here, ys is also here. So we can collect those together. So we have y of s into s plus a when we factorize the y's. And this is equal to minus y naught can go to the other side. So we have y naught plus g of s. So y of s itself is now equal to y naught plus g of s all over s plus a. Okay. So once we have this y of s, we can then we can do inverse Laplace transform. So inverse, have I been writing these headlines? Yeah, I think I've just been telling the story. Let me just continue with that. Okay. Using the known inverse transform formula, the known inverse transform formula. So we just have of course, the formula is actually the inverse Laplace of 1 over s plus a. We have s plus a down there. It's simply equal to e raised to minus at. So that's already obvious there. So if we use that, okay, we get Laplace inverse of y of s equals the Laplace inverse of y naught plus g of s, okay, all over s plus a. So we can tidy things up there. So this is like Laplace inverse of y of s. Of course, we know that's just going to be y of t. So I'll just still write this out. And here now, we can split this into two. This is the Laplace inverse of y naught all over s plus a on one side, then g of s all over s of s plus a on the other side. And then we have the Laplace inverse of y of s equals the Laplace inverse of y naught all over s plus a plus the Laplace inverse of g of s all over s plus a. So now Laplace inverse of y of s can just simply be y of t, and this is equal to Laplace inverse of y naught. Y naught is constant, so we just say y naught e raised to power minus at because of this a. We know the pattern, then plus so this one now we can't factor it until we know what g of s is. So we can leave it as Laplace inverse of g of s all over s plus a. So until we know what that is, we can't really tidy that up as much as we should. So now let's take an example. Let's take an example. So solve the equation. Solve the equation dy dt plus 3y equals to y of 0 equals 4. So that's what we want to solve. So the first thing is to, step 1, apply Laplace transform. Apply Laplace transform. So that means we have L of dy dt plus 3 L of y equals L of 2 on the right-hand side, right? So L of dy dt is simply s ys minus y naught, that's the first one, plus 3, this is just ys, and this is L of 2. So L of 2 will simply be 2 over s, being a constant, as we know. So so we can continue now to say this is s y of s, then minus y naught. Should I even say it's better, it's more appropriate to say it's y of 0, right? This is y of 0. Thankfully, we've been given y of 0. Y of 0 is 4 in this situation. So we have sys minus 4, okay, plus 3. Okay, I can open that up if, in fact. So sys minus 4 plus 3 ys equals 2 over s. So ys is common here as usual. Let me change the colors. Ys is common here, so we have y of s into s plus 3, and that is equal to 4 plus 2 over s. So we have y of s into s plus 3 equals LCM here is okay. Okay, I mean, let me follow the steps. I'm in order, but I just want to make sure I'm following the outlined steps. Okay, so step 2 now, I think. Yeah, that was step 1. So for step 2, solve for y of s. Solve for y of s. To solve for y of s now, from what we have up there, we have s y of s minus 4 plus 3 y of s equals 2 over s. So since we are solving for y of s, so y of s is common there. So we have y of s into s plus 3. Then the minus 4 can go to the other side. So we have 4 plus 2 over s. Be sure that s is not 5. So Be careful about that. So that now we have y of s equals, y of s into s plus 3 into s plus 3 is equal to LCM of this is s. So 1 is s, 4 times s is 4s plus s in s1. So that 4s plus 2. So now we have that we have y of s is equal to 4s plus 2 all over s into s plus 3. That's if we divide both sides by s plus 3. So we have this right now. So, and from what we know already, if we have an expression like this, we can use fraction decomposition to get them to split them up. So, using partial fraction decomposition. So you see the denominator is a product of two linear factors. So we have a simple split. Y of s is a over s. Ah, okay. There's another thing to see here. You look at the top. Okay, yeah, it's the simple thing. Yeah, it's the simple thing. So we have a over s plus b over s plus 3. Okay. This is what I should do for easier handling. So y of s is such that we have 4s plus 2 all over s into s plus 3, and that is similar to a over s plus b all over s plus 3. So again, we can multiply through by the LCM. So we have 4s plus 2 equals a into s plus 3, b into, that's bs in short. And we can use cover-up method. Using the cover-up method. So that helps us to get rid of terms. So using the cover-up method, for s equals 0, if we set s to be 0, b will be gone. So we have 4 into 0 plus 2 on the left-hand side equals a into 0 plus 3 plus b into 0. So b will just go, and then you have 0 plus 2 equals 3a. So a is basically 3 over 2. So that's what a should be. If we want to get rid of a now, we can set s to be minus 3. Okay, so we can set we say for s equals minus 3. On the left hand side we have 4 into minus 3 plus 2. 4 into minus 3 plus 2 is equal to the right hand side, a into minus 3 plus 3 plus b now, s is now minus 3, right? So that way we can get rid of a, because a times 0 will be gone. 4 times minus 3 is minus 12 plus 2 equals minus 3b. Okay, so minus 12 plus 2 is minus 10 equals minus 3b. So b alone is 3 over 10. Okay, so we can go back to the original expression. We can say, so 4s, that was ys, right? So y of s, which is 4s plus 2, I think. Yeah, 4s plus 2 all over s into s plus 3 is now the same thing as a over, the first one is a, for me it's a over s, right? So a is 3 over 2. So that's 3 over 2 all over s plus 10 all over 3 over s plus 3. So that means we have 3 over 2s plus 10 over 3 into s plus 3. So that is what ys now becomes. Okay. So with that in place now, we can then go for step 3. So far we have done step 2. So in step 3, we take the inverse finally to get our results. So step 3, apply inverse Laplace transform. Okay, so using known, okay, there's no point. Let's just look, let's follow the method the way it is. So we have L inverse of y of s, which is equal to L inverse. So distributivity goes, or what, linearity, right? So L inverse of 3 over 2s, okay, then plus L inverse of 10 over 3 into s plus 3. So that's what we have there. So that means we have 3 over 2 L inverse of 1 over s, because that's constant, right? Plus L inverse of, or better still, 10 over 3 L inverse of 1 over s plus 3. Okay. So that means we have 3 over 2. L inverse of s is simply, L inverse of s is just 1. Yeah. L inverse of 1 over s is 1, because L of 1 gives us 1 over s. Okay. Then plus 10 over 3. Then L inverse of 1 over s plus 3 is e raised to power minus 3t, like we know, from recognition of what things we've done in the past. So with all this in place now, of course, L inverse of y of s is also y of t in the time domain, y of t. So we can say, so y of t is equal to 3 over 2 plus 10 over 3 e raised to power minus 3t. So that's the solution to that problem. And you can see this particularly works for initial value, boundary value problems. So this approach systematically transforms the problem, solves it algebraically, and then converts it back to the time domain. So with that, now let's talk about some practice questions. So practice. Solve the following using the Laplace transform. Okay, number 1, dy dt plus 5y equals 0, y of 0 equals 2. Number 2, dy dt plus 4y equals 3, y of 0 equals 1. Number 3, dy dt minus 2y equals e raised to power minus t, y of 0 equals 0. Number 4, dy dt plus 6y equals 5 e raised to power minus 2t, y of 0 equals 4. Number 5, dy dt plus 3y equals t, y of 0 equals 2. Number 6, dy dt plus 2y equals sine t, y of 0 equals 1. Number 7, it gets more complicated, but then it's okay. Dy dt equals, dy dt plus y equals e raised to power minus 3t sine 2t, y of 0 equals 0. Number 8, dy dt plus 4y equals e raised to power minus t plus cos 3t, y of 0 equals 1, like that. So yeah, try your hands on this. Let me see your answers in the comment section, either on Facebook or on YouTube. Okay, let me also know in the comments how helpful these videos are for you. And if you'd like to teach a problem or solve a question, then feel free to like and share this so that more people can have access to it. And if you have not subscribed, please go ahead and do that right now. And for everybody who has subscribed, thank you for that. And everybody should also remember to hit the notification bell so you can always get alerted each time a new video is released. In the next video, I'll be talking about how to use Laplace transform to solve second order differential equations. So that's advancing this beyond what we currently have, and you don't want to miss any of that. So keep aware of when videos are uploaded here. Do maths right till I come your way again. Bye.